So the lab this week is only a 1-week lab. Some of you have found that out, which means we're going to have 1 week off from the lab. However, we're going to take that week off the last week of lecture. I know some of you in lab yesterday were told that you don't need to show up next week, but we're going to change the schedule a little bit. So you're going to finish lab, what is it? Are you on 4? Yeah, you're going to finish lab 4 this week entirely. You're going to write it up and turn it in. And we're going to move this week's homework assignment to next week. So the problem set will not be due this week. So that means the next lab will be starting next week, the final lab. It'll be lab 5 for 2 weeks, beginning next week. And again, we'll turn in the lab the usual time, the week that it's finished. And we'll move the final problem set a week later than the original schedule. So the final problem set will be due at the very end of the semester. There's no lab the last week of lecture. Yeah. Okay. Glad you like that. So, all right. So, and I'll announce that for those who missed it on Piazza. We'll make the announcement. The problem set, I may add one question or something. I will, if I do, I'll tell you next class. Yeah. But what's on there is still going to be on there. Okay, so you can start working on it. All right. Okay, so let's review what we were doing last time, and we're going to wrap that up. As a review, we first noticed that the 20 questions game, defined loosely to be a questioning game, not necessarily 20, but you want to ask questions and as quickly as possible learn the answer through yes-no questions, that this was equal to prefix codes. So any questioning scheme can be expressed as a prefix code. All right. We also saw that prefix codes implied the Kraft inequality. And the Kraft inequality is the following, that the sum over all the code words of 2 to the negative the length of the code word has to be less than or equal to 1. Okay? And this, we also know that this, if this isn't tight, meaning if it doesn't equal 1, then we have an inefficient code. We could always shrink it down, shrink one of the code words without lengthening the rest. So this should actually be tight, or we know we already have an inefficient code. All right. We also saw that that the Kraft inequality implied that there exists a prefix code. With those lengths. So we're going to do an example here just to make sure that makes sense. So if you have lengths, a set of lengths that satisfy Kraft inequality, you can construct a prefix code. Now, we didn't prove this, but I claimed that uniquely decodable codes were no better than prefix codes. So let's put another line in here. Uniquely decodable okay, and what that means is that you can that no punctuation is needed to read out the information. Okay, so if you're thinking of these codes as using them to store information in a sequence, uniquely decodable means whatever your code is, you could read it out. You don't have to know where one of the symbols ended and the next one began, because we're not afforded that luxury of having punctuation in our memory. That would cost some overhead. So the cool thing is uniquely decodable also implies Kraft. That's where we get that I didn't mention this last time, but you can show that if it's uniquely decodable, it also implies the Kraft inequality. And once we have that, we know that uniquely decodable is no better than prefix. Because if uniquely decodable lengths satisfy Kraft, then we could create a prefix code with the same length. Okay? And be just as efficient. So that's really the argument there. So that would mean that in some sense, following through this chain, uniquely decodable implies Kraft. Kraft implies the existence of a prefix code with those lengths. Okay. So. Say. Okay. So the bottom line to remember here is that we just basically have an equivalence. 20 questions is equivalent to prefix. Prefix is equivalent in some sense to uniquely decodable. And they're all equivalent to the Kraft inequality. But you have to remember that equivalent, and there's some nuances to what we mean by equivalent. I mean, clearly not all uniquely decodable codes are prefix codes. All right? But what we mean is, in terms of optimization, they're equivalent. You could easily find one just as good that's a prefix code. And if you satisfy Kraft, then you can create a prefix code. If you have a prefix code, you satisfy Kraft inequality. So these are all basically equivalent if you keep in mind what equivalent means. All right. Now, to illustrate here, this can be found by embedding in a binary tree. So we'll do that example momentarily, but let's recall a few other things. Overview. We saw that the Kraft inequality implied that the expected length of x is greater than or equal to the entropy. So this is entropy. Okay, we saw that because if you just take Kraft inequality, you ignore the fact that the lengths have to be integers. You can solve this optimization in a straightforward way and find that the minimum would be the entropy. And a couple of notes here. This is achieved. Oops. If okay, so if we don't require Lx to be integer, of course there's not a coding meaning of that, but then you would achieve this by setting L of x equals log base 2 of 1 over p of x. Okay, so that's what you would set all the L's to equal. And when you do that, you do satisfy Kraft inequality. Okay, you can plug that straight into Kraft inequality. 2 to the log cancels. And you get a sum of 1 over p of x's. An expected value of 1 over p of x's. And you're going to get a px over px. Those cancel. Oh, sorry. No, you just get a sum over p of x's. Yeah. It equals 1. Okay. So now another thing to keep in mind is that this is achieved if these values just happen to all be integers, right? Okay, so if those are integers, then fine. You achieve that you can create a prefix code with those lengths, and it'll achieve entropy. It'll be the best one. So in that case, we know the best code. There we have it. Special case solved. If these are all integers, then you make the lengths equal to this. Okay, so you have what's referred to as a Shannon code. And the Shannon code is the following. I'll use a subscript S. The lengths for the Shannon code are simply take these values, log base 2 of 1 over p of x, and round up. We'll use that notation for rounding up to the nearest integer. Okay. Since we rounded up, it's still going to satisfy Kraft inequality. They're integer lengths. You can make a prefix code. And we know that this code, the expected value of the Shannon code length, is going to be less than the entropy plus 1. Because all we did was round up. We can only make it up to 1 length longer. So that is a simple concrete code. Well, concrete, we know the lengths. We haven't yet specified what the code is. But that achieves within 1 bit of our lower bound, okay, which is the entropy. So we know the best code, whatever it is in that gap somewhere. Now notice that that this does not even, in most cases, let's say if rounding occurs, then this won't even satisfy Kraft inequality. It'll satisfy it. It will not be tight. It will not satisfy it with equality. Okay, so if rounding occurs, then Kraft is loose. And therefore, the Shannon code cannot be optimal, right? Because if Kraft is loose, it's inefficient. Okay, so here we have this simple code, and we know it's not even optimal unless you're in that special case. So optimal is optimal if and only if these are all integers, right? Then it happens to be optimal. Okay, so let's do an example of the Shannon code. Let's let our space, the values that our random variable can take is just these 4 values, x3 and x4. Okay, 4 possible values, and their probabilities. P of x1 is a 6th. Third. 6th. And a 3rd. Those are the probabilities of each of them. Let's see what the Shannon code says to do. It says let's let the length of x1 equal round up of log of the inverse of 1/6, so log 6. That equals 3. Okay, so the length of the first one will be 3. Length of x2 will be 2. Length of x3 will be 3 again, and here will be 2. Okay, you can check that satisfies Kraft. We don't need to, though, because we know. All right, now, I've kept saying that we can then create a prefix code. So let's create a prefix code. Here's one way to do it. You just greedily go take up leaves in a binary tree. Remember that the symbols x1 through x4 are going to be leaves of a binary tree, and that can define a prefix code for us. Okay, so what we can do is we can just greedily go, let's take the first edge. Let's say here's the root of the tree. We have a 0 down here, a 1 down there. If we keep taking the 0 branch till depth 3. Okay, so we want to assign x1 to a code word length 3. right? So let's go to depth 3 here, and let's put x1 right there. All right. Now we want to assign x2 to code word length 2. Means go to depth 2. Depth 2 would be right here. And we need to put it on a leaf at depth 2. But let's just, again, do it greedily from the bottom. Okay, so let's just say, well, we can't put it here because that you can't have a leaf and then a branch coming out. So we'll just do this. We'll put x2 right there. Okay. x3 needs to be at depth 3 again. And we do have a spot at depth 3 right here. We can put this branch and put x3. Okay? And then finally, x4 needs to be at depth 2 again. Well, this whole lower branch is completely taken up. Right? So we have to go up to this branch up here. Let's just go down the 0 path and put x3 right there. Okay? So there, we've embedded these symbols into a binary tree. And that means our prefix code is just the following. Code is like this. x1. So we have x1, x2, x3, x4. And the code words are 0, 0, 0. See, I just follow the branches to get to x1. 0, 1, 0, 0, 1, and 1, 0. And that's a prefix code. All right, so we have a simple way. If we had sorted these beforehand, then we would actually get a prefix code that's in lexicographical order where the binary, everyone's increasing in binary from the previous whatever. Okay, so just did that to illustrate that this connection between lengths and codes. All right, so we can just talk about the lengths because that's all that really matters to us. And there's sometimes more than one way of assigning a code with the same lengths, right? We could easily have switched x2 and x3. The code for x2 and x3 could be switched. Lengths are all the same. The performance would be the same, right, in terms of average length. Yes? Well. Oh, I wrote x3, first of all. Let me correct myself, and then I'll answer your question. That's x4, yes. Okay, great point. So you're saying, why don't we just move that there? What's the point of it being down so far on the tree? Is that what you're asking? Yes. And that's perfectly illustrating that the Shannon code was suboptimal. That would obviously be a better code, right? Because we've reduced the length of x4 without having to increase any other lengths. Okay, that can only be better as in terms of average length. And there we see that the Shannon code, the reason that's possible is because craft inequality is loose. If craft inequality is loose, you'll always be able to find lengths that can be shortened. If craft inequality is tight, meaning if this sum equaled 1 instead of being less than or equal to 1, this sum right here, then you know that any pruning, any shrinking of one length is going to cause other ones to get longer. So you're at least sort of an optimal edge. It may not be the best one for your particular probability distribution, but at least it's a possible optimal code. You can't rule it out immediately, whereas if craft inequality is loose, you can rule it out immediately. All right. So it's interesting that this Shannon code, what's the benefit of the Shannon code if it's always going to be loose? Well, the reason is because it's so easy to bound its performance. That's the only reason to look at this thing. To say, oh, gosh, that gets within 1 bit of the entropy. Okay. It's not optimal, but it gets within 1 bit of the entropy. By the way, Shannon, this is probably one of the least impressive things Shannon did. So I'm not trying to disparage him by bringing this suboptimal code. Really, this is just a tool for analysis to show how close you can get to entropy. All right. So let's look at another. Okay, we'll get to the Huffman codes, which answer this question, but not quite yet. Still, let's just get a sense of this entropy thing. We keep talking about getting within a bit of entropy, so let's talk a little bit more about entropy probabilities for the moment. Okay, so to understand entropy, we looked at binary random variables in the previous lecture and saw that if they're equally likely, you can have 1 bit of entropy, otherwise you have less. Okay, but let's just talk first. Let's look at this. Suppose all x's in your set are equally likely. Okay, well, this is called the uniform distribution. In our quantization lecture, we talked about the uniform over a continuous set. And here we're talking about, omega is some finite set of things. We still call it the uniform distribution. So P of x equals 1 over the size of that set for all x. All right, that's what the uniform distribution is on this set. And so the entropy of this is just going to be, remember, entropy is always expected log of 1 over P of x. But P of x here doesn't even depend on x. It's just this constant value for every x, right? So that's just going to be expected value of the log of size of omega. And expected value, well, if the thing inside the expected value is just a constant deterministic, then this just equals that constant log of omega. So that's what the entropy is for uniform distribution. All right, remember my logs are base 2. All right, if we want the answer to be in bits. All right, I'll work that out the other way, just for those of you who, are not so comfortable with expected values. We could have easily said that we could have written out expected value explicitly, said that the sum over all x's of P of x times the function that we're taking expected value of, log of 1 over P of x. So here's the way of writing out entropy without using expected value notation. And then this would be a sum over x's 1 over the size of omega log of omega. Okay. And now it's a sum over x's, but there's no x's in the formula, so we can split it out. 1 over size of omega log of size of omega, and this sum, all x's, of 1. Right? So that the sum just sums up to the size of omega. And this cancel. Okay. So what we're saying is that if it's a uniform distribution, then the entropy is just the log base 2 of the size of that set. This should remind you of the beginning of our discussion on 20 questions. How large of a set can you resolve with 20 questions? 2 to the 20. So the entropy of a set of that size is exactly 20 bits. All right. Okay. So then what is the entropy of a roll of a die? Okay, it's that's a uniform distribution over 6 values, right? So h of x equals log base 2 of 6. Someone calculate that for me, and I'll write it up here. All right. Someone have it? What's log base 2 of 6? What? Around 2. Oh, what did you say? 2.58? Okay. By the way, you all know that Google is a calculator too, right? All right. I see so many calculators out on the desks. All right. Okay, what if we have 2 dice rolls? So that's that many bits. It's actually important to, when you talk about entropy, to give the units. If you use log base 2, it's bits. Yes? Oh, the expected value of the dice, actually it's 3.5, right? Because if you, right? So the average value you'd get would be 3.5. But it's not just, so entropy is not just expected value of x. It's expected value of the log of 1 over the probability of x. So it's the expected value of a particular function. All right? Yeah, that's what the difference is. So, yeah, what I was saying is if you use, say, natural log, then actually the only difference between your choice of log is that you have to multiply, that there's a conversion factor. You have to multiply by a constant to convert the units. All right? And the units people call for natural log would be nats instead of bits. So you'd have a certain number of nats. I'm not sure log base 10 what units people say, whatever. Okay. So if you roll 2 dice, let's say let x1 be the first die, and let x2 be the second one. Okay. And so what we're talking about here is now outcomes of these 2 dice rolls are pairs of numbers, like x1, x2 equals some 2 numbers, like let's say 1 and 5. That would be one possible outcome of the 2 dice rolls. Think of these dice as being ordered. There's a red one and a blue one, and we're always listing the red one first or something like that. Okay, so then we've now talked about the notion of independence, but let's introduce that here. This is just a probability notion. Independence, so these dice are independent of each other, and by knowing that they're independent, we are able to calculate the probabilities of pairs of things happening. Whenever you have 2 independent things, you could say the probability of x1 equaling something or being in some set, let's say x1 equals 3, and the other one, x2 equaling something, let's say 6, for example, is just the product of the 2 probabilities. x1 equals 3 times the probability that x2 equals 6. Okay, and this is, in general, so in general, if you do not have independent events, you have them correlated somehow, then this second term would be a conditional probability. Now, this is not a class on probability, so we don't really have time to go in depth on this, but I will just comment that whenever you have 2 different random variables and maybe they're correlated, you can calculate the probability of a pair of things happening by looking first at the probability of one happening, okay? And then you have a conditional probability of the second happening given you knew the first one happened, okay? And you multiply these 2 things together. It's a general way of expanding out probabilities of pairs into a product. Okay, it's a chain rule for probabilities. But the second one in the chain might depend on the value that occurred in the first one. So it's called a conditional probability. If it doesn't depend on the value of the first one, then that intuitively that's independence, right? If the next one happening doesn't depend on at all of the first one happening. And that would mean that this would no longer be a function of x1. It would just be the probability of x2 happening by itself. Okay? And so that gives us this formula that independent events, the probabilities of a pair of things happening, is a product of the individual things. All right? So we know that in this case, the 2 dice, they're independent, that the probability, so we can have a probability mass function, and now we would say x1 comma x2, say called the joint probability mass function, and it's just like the ordinary one we had before. This is defined. This is the probability that x1 equals this particular value. Let me use A and B because I know it sometimes confuses you if I have capital and lowercase in handwriting. All right. And x2 equals B. Okay, so it's a joint probability mass function. Anyway, again, this is not stuff you have to master, but this is, I want to get to a point having to do with entropy. So, so that means that what we know here in the dice rolling case is that P of x1, x2 is going to equal 1/6 for the first value, since every outcome has a 1/6 chance, times 1/6 for the second value, because they're independent, right? So it equals 1 over 36 for all x1, x2 that could occur. You know, they're in the numbers 1 through 6. Does this make sense? So it's pretty straightforward stuff. If you roll 2 dice, the chance of seeing a 2 and a 6 is 1 over 36. The chance of seeing a 5 and a 1 is 1 over 36. Chance of seeing a 0 and a 3 is 0. Okay, because you can't have a 0. All right. So, so then the entropy of these pairs, the entropy, this is a uniform distribution. Everything has probability 1 over 36. So what we say is the entropy of a pair here, a comma separating them, is now log of 36. You see, because I'm just taking what we already calculated previously, that if we have any uniform distribution, the entropy is going to be log of the size, right? So the entropy of these 2 dice rolls is log of 36. And what is that going to equal? 5.16. And why do you say that? Yes, it equals 2 times what we had for 1 dice roll here. Because we know how logs work, and if you square the inside of the log, you double it, right? So this 2 times that, 2.58 bits, is what we get for the 2 dice rolls. So we notice a pattern. What's the pattern with entropy? If perfect. Yep. So if you have like an x1, x2, even if you had more, x3, ... are independent, if they're mutually independent of each other, then you would have that the entropy of the whole set of them, x2, x3, ... equals the sum of their entropies. Okay, so entropy has this nice property. This is only because they're independent. Okay, if they weren't independent, you would have something else. Actually, you have something very nice. If they're not independent, then you always have that the joint entropy can only be less than the sum. Can't be more. Okay, so in general, h of x1, x2, x3 less than or equal to the sum, but it's equal if they're independent. Okay, so just some notes on entropy, things that will help us understand it. You have some problem set things with entropy. A lot of them are just asking you to approximate. You know, like you should come up with an educated approximation of the distribution, and then calculate entropy based on your approximation. That would be a good way to do it. Okay. Okay. Any questions about entropy? All right. So let's look at a. So we're going to get to Huffman after we first talk about the Fano. Shannon-Fano code. Okay, so Fano was a young professor in the early 1950s, and Shannon had just invented information theory in 1948, and Fano worked with him on solving this one little piece of information theory on what's the optimal prefix code. Okay, They didn't solve it, but they came up with this idea, which is similar to ideas that were suggested last time in this lecture. They said, well, sort the outcomes by probability. Okay, and then make cuts as close to p equals a half as possible. So, in other words, you would take if you had all these probabilities, here's x1, x2, x3, x4, and if you had things like, let's say they're already sorted, and you had like a 0.4 and 0.2, 0.2, you would start constructing, so these are the probabilities, p of x. You would first say, well, what's the best for, actually this is not very good because the best first cut's ambiguous. Let's do this. Okay, and here you see the best first cut is to get closest to a half, you would isolate the 0.45. Okay, and you would say, you're building up a tree. You're saying on our first question, we're going to put this group here, which is as close to 0.5 as possible in total probability out of this set. We're going to put it along this branch. So up on this direction, we get x1, and on this direction, we get x2, x3, x4. And then we just iterate. We say, okay, let's try to cut. Now that one's done. The top branch is done. And on the bottom, we then say, okay, this is a total of 0.55, half of that. We want to get as close to half of that as possible, right? 0.275. So let's yeah, you're probably going to do what? You're going to take a 0.2 isolated. Yeah, so you're going to isolate a 0.2 by itself. So again, you branch out like this, and you do, let's isolate the x2. And the whole idea here is is at each stage, working from the root, you cut it as close to half as possible. Okay, and that's the Shannon-Fano code. Now, in some cases, you might get lucky and it might be optimal, but this is not going to be optimal in general. So what happened was you get Huffman was taking a class from Fano, and in 1951, he in this class he had a choice either to do a term project or to take a final exam. Everyone had this choice, and the project that he had decided to try to tackle was to work on these codes, say something about them, figure out maybe a better code or whatever, ideally the optimal code. And he felt pretty stuck, so he was about to give up and go study for the final exam. But then he ended up solving it. So it was a nice, he solved the problem that his professor had been working on a little while. And these are the optimal codes. Now, actually, I believe that the way he went about solving this, a good way to try is work with very small sets first. Of course, we want to solve it for any large sets of outcomes. But he worked with small ones and worked through all the different ways of designing prefix codes and checking, in which cases what's optimal, trying to look for patterns. Apparently, he worked through, started with 3 and then 4 and got up to, once you get up to 5 or 6, you're looking at many, many different ways of doing encoding. And so he had pages of derivations and eventually identified the pattern. Okay, and here's how you construct the Huffman code. You start by sorting. Let me do a real example. So let's, so the Huffman codes, in a nutshell, the principle is you design the tree from the leaves. Okay, so I'll work through an example and it'll be apparent how you actually do this. Suppose you, okay, so let's let omega be just 5 values for this example. A, B, C, D, and E. I'll stick with the convention I've been using. X1, X2, X3, X4, and X5. And let's say we have, for this particular example, we have, here's P of X in a column, and let's say we've got, say we have these probabilities. Now, I've already sorted them. So first, let's say, start by sorting. Okay, so I'm just going to write them down sorted. This is 0.25, 0.25, 0.2, 0.15, 0.15. Okay, so notice they're sorted, greatest to smallest. Okay, so that you have to do that first. Okay. Then what you do is you say the least likely code words. It makes sense that I would distinguish those last. Okay, that I could design my prefix code so those have the longest lengths, and my last question decides between those two. Okay. You can prove that this is actually the optimal way to go about, but just try. We're not going to prove it, but it does make some sense that you would try to resolve those two last. And so what we're going to do is we're going to combine them. We're going to write our tree backwards from the leaves first. So the last thing would have been to distinguish those, so we combine those. Now, if you combine those, we have to add their probabilities. The probability that one of those two happens is 0.3. So what we do here is we actually, okay, so we're going to combine these and make a single outcome of probability 0.3 and resort the list. So that 0.3 is bigger than anything in our list. So we put the 0.3 in its place in the sorted list. We move everything else down like this. Okay. See what I did? I just combined the least two likely and then resorted the list and put lines to identify where everything went. All right. Same thing here. We take these two least likely outcomes. We get a 0.4. That, again, goes to the top of the list. It's not always going to have to do that, but in this example it does. 0.45. Okay. And then we combine these two, and that gives 0.55, 0.45. And then there's only two left to combine. 1. Okay. Now what we've constructed here is the binary tree for our code. All we have to do is grab it by the root and shake it out because it's all tangled up. All right. So the easiest way to do that is to just put labels. Here was a, let's say 0, 1, 0. Every split we have to label 0 and 1 somehow. Okay. All right, so now what we can do is we can construct, let me put a column here. So the result of all of this is, let's put our code words. All right, so x1, the code word for x1, well, let's just follow the whole branch of x1 to the root. But then we have to write, of course, everything's backwards, so we're going to write it in reverse order. But what we have here, this is not a branch, so it doesn't give us a bit. But, and you have to be, in my drawing, that 0, you just have to know the 0 was on this that branch. Okay, so x1, there's nothing, nothing. And then here we have a 1, a 0. So it's 0, 1. Okay, x2, we go along this branch. We have a 0, nothing, 1. So it's 1, 0. You see that? x3, we have, again, nothing, and here we have a 1, nothing, 1. All right? And here we have 0, nothing, 0, 0. And finally, 1, nothing, 0, 0. So there's our prefix code. Okay, so that's a construction for the Huffman code. Now, in fact, what's important, because there can be many ways to rewrite an optimal code, because we could go swapping code words of the same length, and it's not going to change the performance, right? So what really you get out of the Huffman code is the lengths. So we can put here length L. And the lengths were 2, 2, 2, 3, 3. And the important thing is that an optimal code should have those lengths. You can come up with other optimal prefix codes that have those lengths. Fine. What we really get is the lengths of the Huffman code. Okay, or you could use this exact one we got out of our construction. That's fine. Any questions about how to do a Huffman code? Any aha moments? How come you couldn't guess this in the 20 questions part of last lecture? Okay. So let's, by way of looking at some applications of things we learned, let's talk about JPEG encoding. Now, this part of the lecture, it's sort of like when we talked about things like MRI. This isn't what you need to take away from this is not necessarily the details of how JPEG works. Not going to be, you'll see in the problem sets what kinds of questions we want you to be able to actually solve, and we're not going to ask a lot of specifics about things like JPEG or like the last thing in the lecture today if we have time. But what we do by talking about these is we kind of glue together the pieces you've learned. Think about principles you've learned in different ways, and so I think JPEG is a great example to help with that. So what is JPEG? You guys know what this is. Images are often saved as JPEGs. And you usually get some nice compression out of them. They're used a lot on the web because you care about how big the images are for download speed. Okay? And they work very well for natural images like photographs, things like this. There are some types of images JPEG doesn't work well on. If you did the lab yesterday, you experimented with some of these JPEG-type principles, and you saw some images don't work very well. What kind of images don't? Yeah? Yeah, with really sharp edges. Like, for example, if you have text. Okay, text, you'll notice the artifacts in text more than you will for other types of images. But let's talk about how does JPEG do this compression, because it's going to touch on all sorts of little things we've talked about, quantization, Fourier transform, the Huffman coding, and so forth. Okay? So the first thing to talk about is that, first of all, color is three-dimensional as perceived by the human eye. So it's interesting that you've all experienced this notion that you can mix, three colors together and kind of form any color you want. That's what computer monitors do to make colors. That's what you do in art. You don't necessarily just use three, but there's, we talk about there being primary colors. All right. Yet, as you think about physics, you say, well, how does this make any sense with the fact that light is on a spectrum? We have some visible spectrum, but there's no three in this picture, right? I mean, where's this 3 dimensions, 3 primary colors coming from? Any idea why are there three primary colors? How does that have anything to do with light and physics? Yes. Exactly. Exactly. So our cones in our eyes have three different types that are sensitive to different different spectral shapes. Okay, and that's the whole reason why color to humans can be described in a three-dimensional way. In other words, we can mix three colors together and get ourselves to see any color we want, right? So some animals have more or fewer types of cones. Some animals can see richer, four-dimensional color and so forth. Color, if you're colorblind, you have a lower dimension. All right. So what is done, first of all, is, so for example, you can, since it's three-dimensional and there's some linearity involved, you can represent this as a basis. For example, often you say, so red, green, and blue are pretty well matched with the actual spectrums of the codes in your eyes. But you can also, use another basis for colors. It's often said that red, yellow, and blue are primary colors. And these are just different examples of a basis that would span the colors that you can see. Yeah. Okay, there's another representation. That would be this. People represent it with these letters, and this is what JPEG does, where Y is the intensity, and CB and CR represent how much the intensity is pushed towards red or blue. Okay, so this is like a color aspect, but it's not just the brightness of color. It's kind of like saying, qualitatively that intensity is kind of bluish or reddish. And between these three, of course, now you have a three-dimensional representation. You should be able to use this to represent colors. Okay, so what JPEG does is first separates out the colors in this way, so it just transforms whatever you had for color representation into these three. All right, and the reason it does that is because intensity apparently will notice the fine details of intensity much better in an image than we will the fine details of the color. Okay, so the first reduction that is done is you usually downsample. I'll use a different color. You downsample the color parts and not the intensity part. So this would involve, taking fewer pixels, basically. Perhaps low-pass filter first and take some fewer pixels. Okay, so that's the first reduction. By the way, this type of stuff about the eye and the colors they see, in Kulkarni's notes, chapter 6, there's some nice discussion on this if you're interested on the website. Okay, so the next thing that's done is, now each of these three, it's like you have three separate images. They're each going to be compressed separately. Okay, and so let's say compress. Okay, so the next thing is you split the images into 8 by 8 blocks of pixels. Okay, so what that means is, let's say you have an image of here's your picture, and you have like a tree like this. Okay, you're going to take a little block, 8 by 8 pixels, and you're going to compress each block separately, and then in the end we'll piece it all back together. All right. So so from now on we're just talking about these standard 8 by 8 blocks. Yeah, so technically this is 8 by 8 on the downsampled space, and so you'll have, to keep it aligned, you'll have something like 16 by 16 up here. If you usually downsample by only a factor of like 2 or something, let's say by 2. Okay, so you will actually have bigger blocks for the y, 16 by 16 or something. Okay, now what you're going to do is a discrete cosine transform. Now, we have not done the discrete cosine transform, but the good news is this is just like, so think of this as a DFT. Okay, so we've turned our 8 by 8 block of image into an 8 by 8 DFT, where the low frequencies are up in this corner, low frequency in both directions, and the high frequencies are over here. Okay, what's down here? Exactly. So this is going to be low frequency in the horizontal direction and high frequency in the vertical direction. Okay. Okay. So we had an 8 by 8 block of image. Now we have an 8 by 8 block of DFT. I'd like to stop for the moment and actually talk a little bit about the discrete cosine transform. Not because you need to know discrete cosine transform, but because it'll be interesting, and we'll get back to the DFT. You thought you had a break from Fourier, but I'm going to sneak it in. Okay. So again, really, you can just think of this as a DFT. All the intuition goes through. All right, but technically, a discrete cosine transform. First of all, it's always real. It's not complex. Okay, but secondly, it's a sort of a signal processing trick. And let's talk about what happens in the DFT that the DCT tries to avoid. Okay, remember. So here's the DFT. Let's just talk in one dimension. All right. A DFT of a one-dimensional signal. Let me draw my signal here. Something very simple like this. Okay. So suppose you have a signal like this, and it's really discrete, but so many points I'm drawing it like it's continuous, right? But it's a discrete in time. And you do a DFT to it. Okay. DFT, remember, is equivalent to the Fourier series, discrete time Fourier series. All right. So what's going to happen is, so let's think of this as a discrete time Fourier series. Now, what does the discrete time Fourier series try to do? It tries to represent this with sinusoids. And looking at this, I've drawn such a simple signal, you would think only a couple of sinusoids could actually create this. And I believe that's correct. You could just have a couple of cosines with the right shifts, and you could get this signal. But the problem is, oh, boy. Okay. But the problem is that the Fourier series has to align those cosines with the window. All right? So it's only going to look at cosines that have the same period as this window. And that's not going to work well for this particular drawing, because notice I've aligned it kind of strangely, right? So the best way to understand this is to remember that the Fourier series reconstructs the periodic extension of a signal, right? So let me draw the periodic extension of this signal. I just repeat that signal here, like this. Boy, not the best picture, but you get the idea, and then I repeat it again. Okay, now it doesn't look so beautiful, right? Because it's got these jumps. All right, and so this is another way to understand why, when you take the DFT of this thing, you're not going to get just a few simple cosines like you initially might have thought. Because now you're actually trying to get cosines that reconstruct this with the jumps here, these discontinuities. Right? Okay, so of course, to get these discontinuities, you're going to need a sum of an infinite number of cosines at just the right values. Do you remember doing this in Lab 2? In Lab 2, you took a sinusoid that wasn't quite aligned with the window. You looked at the DFT and you saw it wasn't just the tones you created, it was a bunch of other things. It was exactly this problem, not lining up your simple sinusoids with the window length. So the best way for me to think of what's going on there when you take a DFT of something that's not aligned is just think of the periodic extension. You have these discontinuities. So really, because the Fourier series has to do with the periodic extension, you should always be thinking of the edge of your window as wrapping around. And if they don't meet up, that's going to cause some artifacts, right, in your Fourier transform. So the discrete cosine transform, what it actually tries to do is it first repeats your signal you're trying to analyze. Let me do this. Sorry. It repeats it mirrored. So it goes like this. It takes what I had drawn, and then it first repeats it backwards. Okay, there. I doubled the length. Repeat it backwards. And then, equivalently, you now take a Fourier transform. This is going to do two things. It's going to make it even, so it's going to make the Fourier transform be real. Okay, but it's also going to, now, of course, still the DFT of this is still going to repeat this thing, but notice it's continuous now at the edges. Okay, this doesn't avoid every artifact. You're still going to get discontinuities where these things meet. I mean, you're going to get, look what's going to happen. This is going to go, it's going to be sharp. So even though it's continuous, it's still non-differentiable usually at the edges. So you're still going to get some artifacts, but the intention is that it's a little bit less problematic. Okay, so that's the discrete cosine transform. Anyway, it's not really a big deal in terms of understanding what's happening in the in JPEG here. So it uses this discrete cosine transform. All right. Okay, now the next thing it's going to do, the reason you do this cosine transform is because if you're trying to compress something, think of an image. Pixels next to each other are very correlated. Often they'll be the same color, right, if you have a high resolution image. So what you'd like to do when you compress is that correlation, you'd like to take advantage of it. And one way to do that is if you can transform in such a way where the correlation all kind of clumps together on just a few elements, then that's going to help you in compression. So when you do the Fourier transform, what's been noticed is that the images, most of the correlation shows up in low frequency components. So you get a lot of the energy of your image here in the low frequencies, and much less important detail happens out here. Okay, so you've sort of concentrated, taken advantage of the correlation, and moved it to one location, ready for better compression. All right. The other thing that's noticed is that the eye is not so good at perceiving noise in the high enough frequency noise. Okay, so you might not even notice. If we have to do some lossy quantization here, if we use fewer bits at the high frequencies, it'll be more tolerated when you look at the image. Okay, so that's the whole idea is, okay, the next step here is to, I'm going to get rid of, this was an aside, right? So let's just kind of isolate it like this. Okay, so we're still talking about JPEG here. And the next idea is quantize uniformly. So uniform quantization, meaning each number here, remember there's 8 by 8 numbers. Each number is uniformly quantized, however, with different precision. Better precision used for low frequencies. By better precision, we mean essentially use more bits to quantize over here and use fewer bits here. If you use fewer bits, you have more spaced out quantization points. If you remember our quantization discussion, you're going to be introducing more noise. But that's by design, right? Because we're assuming noise here can be tolerated more than noise here. Okay. Technically, the way you do this quantization is very simple. You first scale each entry by different values depending on where they are. And then you round to the nearest integer. Okay, so technically that's how you can do this quantization. Okay, so what that means is you have a bunch of numbers. These are fixed numbers. They have nothing to do with your image. Okay, they just have to do with the JPEG standard. These numbers would say how much to scale each value by. So you have some matrix, like you have some numbers. So this DCT is a bunch of numbers. You have an equally sized matrix of numbers that say how to scale. So this might be 16 up here, 18, and maybe down here it's like 50, 100, 50, and I'm just filling in some of the values. You have this matrix of numbers, and that says basically you're going to take your DCT, you're going to divide each value by the number in this matrix, okay, and then you're going to round to the nearest integer. So this is the lossy part of JPEG. There's only two lossy things in JPEG. The first one was this downsampling right here. We downsampled. That's lossy. Okay. The other lossy part is this quantization. It's the whole thing. Okay. And this is basically saying the bigger the number is, the more noise you're introducing. Yeah. And so this is basically saying how much noise are you introducing by your quantization. But you're doing it on purpose because you're going to save bits by introducing more quantization noise. Okay. Now, once you've rounded these to integers, now you just have a bunch of integers. Of course, to undo it, in the end, when you want to reproduce the image, you're going to take your rounded numbers, you're going to multiply them rather than divide by these scaling constants. You're going to do the inverse DCT and put it all back together. Okay, and it'll have some noise. So the last steps are to do lossless compression. Now we have a bunch of integers, and we just need to store these as bits, and we want to do it in a nice, efficient way, losslessly. Okay. So that is done through two steps. First of all, you should notice, so JPEG last steps, lossless. So we have a table of integers now. So we have quantized DCT. Discrete cosine transform. That's this table. All right. Now, what we do is we do two steps. The second step will be Huffman codes. The first step will be what's called run length codes. So you'll notice something interesting is going to happen because we quantize so coarsely for the high frequencies, and because the high frequencies had less power to begin with. A lot of these values will just be exactly 0. Okay, so when you actually do this quantization, you'll have a bunch of actual integers up here. You'll have a bunch of zeros down here. Okay. So now, to take advantage of this and do lossy compression, what you want to do is you want to be able to describe where the zeros are in an easy way. All right. So what's done is you have this path that's been defined. It just zigzags through these numbers like this. And you write out all the integers in order of this path. Okay, so now we have a long sequence of numbers. The reason we do this path is because now we expect to have a lot of zeros be in a row, because it's going to start hitting a lot of the zeros down here towards the end of the path. We'll have big, long strings of zeros. All right. So the first thing you do is you run length code. And that's basically a way of saying very efficiently, oh, I have 8 zeros in a row. I have 20 zeros in a row, or something like that. Just as an example of a run length code, if you have something where you expect to have a lot of 1s and a lot of zeros in a row, in the JPEG case, you just expect to have a lot of zeros in a row. Let's say you have something like this, a sequence like this, and you want to describe it efficiently because you know that the 1s and zeros are clumped. You can just say, well, I have 5 1s, and then I have 1, 2, 3, 4, 5, 6, 7 zeros, and 6 1s, and 4 zeros, right? And in fact, if I know they're always alternating, I know they're 0, 1, I could write this even more concisely, something like 5, 7, 6, 4, as long as I knew it started with 1s. Okay, so that's just the idea of run length codes, combining a lot of similar things in sequences. All right. So you do a run length code first, according to some protocol here, and then finally you have a bunch of integers that you do a Huffman code to compress. So there's a run length code followed by a Huffman code. So the statistics of images in general are used to figure out what the probability distribution is of these numbers, and then a Huffman code is designed. Okay. So that's it. I mean, things we've learned. We just pieced together a bunch of things we learned. Fourier transform. It kind of concentrates all the correlation into a few components. Quantization. And then lossless compression. Here. And that's JPEG. Now, any questions? Yeah. Oh, then what you do is you actually go, they put some padding around the edge of the image. I'm not exactly sure what's used, whether they just put like a random padding or what's put around the edge. And then they compress, and then they somehow keep track of how big the image should actually be for when they're going to display it. Yeah, good question. Okay, so the topic that I'm going to talk about for the next 5 minutes, and we'll talk about next time, is the opposite of compression, sort of. Okay, compression was taking your information and squeezing out all the redundancy, right? Especially lossless compression, to make it just as concise as possible. So the other side of this is error correction. And this says, forget about where our information came from. Just treat it like bits that need to get somehow either written to memory and read back later or transmitted through some environment. And you're afraid that errors are going to affect the process of getting the information back. So now we do the opposite. We go and we put in redundancy into our signal to combat the errors. So it's sort of totally complementary to compression. All right. Now, the technology you use every day uses error correction and error correcting codes. And we're going to go through some cool examples of this next time. But just as by way of example, there's a particular code known as Reed-Solomon codes. These were invented like 4 decades ago. All right. But they're everywhere in technology. So, for example, CDs, let's say. A CD actually has, you took digital data and you wrote it using a laser onto a CD that can be read back, a bunch of zeros and ones. But it actually has redundancy written right onto the CD. In fact, 1/4 of the bits can be considered redundant on a CD. So the rate of the Reed-Solomon codes on CDs are 3/4 codes, meaning only 3/4 of the space is used for actual information. 1/4 is used for redundancy. But the redundancy is in a way that's much cleverer than you might imagine. It's not like redundancy is... The redundancy allows you that if you lose bits, even the bits of the actual information, right, you can recover them because of the redundancy. It's not something as simple as repeating the bits here and there. It's a very clever way of encoding redundancy in. So what that means is that on a CD, if you have a scratch, the error correcting codes are so good that scratches will rarely lose your information, although they will lose actual bits from being read by the laser. Okay, so physically, a scratch can prevent many bits from being read. So bits will be read in error on the physical level where the laser is reading. But information that the software pulls out of the CD could have complete information in almost all cases. In fact, when a CD has an error, it's usually because of something very different. It's usually because of the tracking. The laser has to go track these paths around the CD. The scratch causes the tracking to skip over. And that causes, let's say, problems when you're reading out CDs or DVDs. But the error correction is hardly ever the problem because it's so much redundancy on there. The Reed-Solomon codes are actually used not only in CDs, but DVDs, cell phones, almost every cell phone standard. Now, there are other error correcting codes besides Reed-Solomon codes, but you find Reed-Solomon codes in deep space communications and all sorts of things. So they're actually very pervasive. And So next time I'll spend just a little bit of time on Reed-Solomon codes by talking about like how exactly they're structured on a CD, for example, to combat errors. And then we'll go through some simpler codes that we can actually understand the math of very easily.